Hello everyone, welcome to In 5 Minutes. In this video clip, we will discuss next problem on series parallel connections of resistors. The question is find the equivalent resistance between the terminals X and Y for the network shown below. So these are the two terminals between which we have to find equivalent resistance, which can always be done by combining the resistors in series. The resistors values will be added, and for two resistors in parallel combination, the equivalent resistance will be the product divided by the sum. So in looking at this particular network, let us figure out which resistors are in series and which are in parallel. If you carefully observe, you find no two resistors in series, but there are two resistors in parallel. So we'll start from there. Two resistors are said to be in parallel if they are connected between the same two ends. So you can see this 8 ohm resistance is connected between these two particular ends. These two lines can be taken as two nodes, and this 8 ohm is also connected between the same two lines or nodes, and hence this two 8 ohm resistors will be in parallel. So when two resistors are in parallel, I will simply combine them. These are of equal values. Equal values resistors in parallel will have equivalent resistance, which is half of the original value. So 8 parallel 8 will be 4. There will be only one 4 ohm resistance in between here. So let's draw the equivalent circuit and see how does it look like. Starting from node X, I'll call it 4 ohm. So this 8 I've combined, I've connected here a 4 ohm resistance, and that means no 8 ohm will appear here anymore. So let me draw the remaining circuit now. Now, if you're already comfortable with clubbing resistors, those are in series and parallel, you can in one step also consider multiple such combinations and go on replacing with equivalent values. What I'm trying to tell you is we could have also taken these two resistors. As you can see, they are also in parallel, but never mind, you can always go to the next step and club two new resistors. So now the two new resistors that I'm going to club will be this 8 ohm and this 8 ohm. Rest of the resistors remain as it is. So these two are in parallel because once again you can see this node is common and this node is also common. These are the two ends of two 8 ohm resistors. Again, in parallel combination, it will become 4 ohm resistance, and I will show only one 4 ohm resistance and remove two 8 ohm resistors which are in parallel. So let me draw the equivalent circuit here itself. I start with node X with 4 ohm resistance. Now what I'll do is I'll remove this particular 8 ohm resistance, and I will only one resistance which is 8 parallel 8, that is 4 ohm. So this is one node. So what I'll do is I'll just replace this resistance with 4 ohm. You can replace any of the two resistors with the equivalent resistance and remove the other resistance. This is what you can always do whenever you are dealing with two parallel resistors. So this is what we get. This is 8 ohm and this is also 8 ohm. Now, so this is what we get after the second step. Now, if you observe, if you try to find out two resistors in series or parallel, you don't find any such pair, because no more two resistors are in series or parallel in this particular circuit. So the question is how to proceed in such type of situations. One option is you can apply star delta transformation that we are going to discuss later on, but right now it is not required because we are going to use the concept of balanced Wheatstone bridge. According to balanced Wheatstone bridge, first of all, what do we mean by Wheatstone bridge? Wheatstone bridge is nothing but when we have four resistors connected in this fashion and one resistor connected in between, it forms Wheatstone bridge. Now when the bridge is said to be balanced, so if I quickly draw another circuit which looks something like this, this is nothing but also the Wheatstone bridge. You can see the shape can be anything, but the condition is that you must have these two resistors connected from this end, R3 R4 connected at this end. This is what we have: 4 ohm 8 ohm connected at node X, 4 ohm 8 ohm connected at node Y, and from the other two ends of the resistors there is one extra resistance, which is what we have here. Again, let me call it R. So the bridge is balanced if a condition satisfied, which is R1 by R2 is equal to R3 by R4. That means the ratio of these two resistors must be equal to ratio of R3 by R4. If these two ratios are same, in that case this resistance becomes redundant. That means it will not carry any current. Current through R1 will directly flow through R3, current through R2 will directly flow through R4. In other words, R1 and R3 will be in series, R2 and R4 will be in series. So the circuit that we have, in this case my R1 can be 4 ohm, this can be my R3, my R2 can be 8 ohm here, and this 8 ohm can be R4. So now if you take the ratio R1 by R2, on this side it's 4 by 8, which is half, and on this side R3 by R4, it is again 4 by 8 equal to half. That means the ratios are same, and because of that this middle branch 4 ohm will become redundant, it will not carry any current. So applying this concept of balanced Westone's bridge, we will now draw the equivalent circuit. We have, as you can see, removed this middle branch because that middle branch will be redundant resistance, and these upper two resistors 4 ohm will come in series. Similarly the lower two resistance will also come in series, and therefore the resistance between RXY will be 4 plus 4 will be 8, and that will be in parallel with 8 plus 8, which is 16. So this parallel combination will result into 5.333 ohms. So that's the final answer.